Hello everyone. In this video tutorial, we will show you how to use the multi-processing capabilities of your PC. Normally, when you develop an application, most of the time it is going to be use a single processor. Even if your computer is actually having multi-process, it will not use that. For example, let's say my PC. Let me take it. Manage. So there might be something. Just a minute. So if you take the case of your device manager, if you take device manager, you can see that just a minute. You can see that there can be multiple processes in your machines. Let me show you that as well. Where is that? See this. So even if so let's say this in my PC there is actually 1, 2, 3, 4 core processes. Okay, actually there, but unfortunately, if you didn't program it correctly, if you normally do a program, it will be using only one processor. So in order to use multiple core processes, you need to program it in that way. For that, there are a lot of other packages are actually available. One such package is OpenMP, Open Multiprocessing. Okay, so we need to make sure that you are actually first supporting that OpenMP package, OpenMP in your C++ compiler settings. Then you need to program accordingly based upon the OpenMP settings. There are other directives in the program, parallel directives in the program, where you will be able to take advantages of that parallel computing environment, or you will be able to take advantage of multiple processes. So let's see how it can be done. Okay, so go to Visual Studio, then you create a new project. Okay, just click on the create new project. So we will select a Win32 console application here. Okay, so let me try to open it. Win32 console. Okay, C++ console or so we will first check the C++ console application. Where is that console? So C++ hello world. Okay, console app. Okay, so let's try to run this C++ console application. Click next. Maybe what we will do is multi-proc. Okay, multi-proc. So like that, we will name the application. Then maybe if possible, I just want to show you one more feature like assembly, how to call the assembly instructions as well. So let me put it as ASM as well, assembly. Okay, so let's try to create a hello world application with this. Okay, so let's wait for that. So we actually created a hello world application. So if you try to run this application, let's try to run this application. You can see the hello world. Okay, just let me run the application. Let's confirm that it's actually display hello world. Yeah, it displays hello world. Now what we will do here is we need to change the settings of this multiprocessing application. So how can we change it? So there is a switch, compiler switch, where we will be able to make use of that thing. Let me see where that thing is. C++, somewhere here, OpenMP. There is a optimization. There is a switch called OpenMP. Code generation. Let me see. Language. Yeah, OpenMP support. See this. Okay, so what I will do here is I will put /OpenMP in the compiler settings. So I will put yes, then I will click on apply, then click OK again. Then I will make sure that let me try to run the application again. Okay, so yeah, so again it actually compiled. So what I will do here is I will ask Grok to develop a C++ application which will make use of OpenMP and which will run a normal application as well as an application that support OpenMP. Okay, so in that way you will be able to easily understand the performance difference. Okay, so so what I will do, ask Grok create a C++ application, C++ console application that show create a small C++ console application that show the performance difference when we use OpenMP and when we are not using OpenMP. Okay, so let's see what actually the grok creates. Okay, create a small console application that demonstrates. Yeah, so probably it is actually creating a small console application now. So let's wait for that. Okay, so yeah, so it actually created a console application. So what we will do here is we will copy it. Okay, then we will paste it here. Okay, so let's let me yeah, so let me paste it here full. Okay, just paste it. Yeah, so let's see what actually the program does. Probably they might have already explained it in the bottom. So no, they didn't explain it. So it is something like a matrix multiplication. Okay, matrix multiplication serial as well as matrix multiplication parallel. Okay, so that's what. So this is what OpenMP parallel for. Okay, so this is a pragma which will indicate that if the compiler is having the OpenMP support, then this pragma will do the things parallelly. Okay, so probably they might have already see this. They have actually a size, vector size. Let me see this multiply. So it is actually a matrix multiplication serial way and matrix multiplication parallel way. Okay, so that's what it actually generated. So let me serial execution time, and it is actually displaying the serial execution time, and it's actually displaying the parallel execution time as well. Okay, so let's try. So let me see what's the size of the matrix. The size of the matrix is 1000 by 1000. Okay, so 1000 by 1000. I don't know how much time it is going to take because we want to explain some concepts. So probably 1000 by 1000 multiplication is going to be don't know how much it will take. Anyway, let's try to run it. Maybe what we will do here, we will try to run it release mode. Okay, so it will make more faster. Okay, so anyway, let me compile it and launch it again. Yeah, so let me see. So what is going to happen? So it's doing something. Let me see why let me see what all things are actually there. The C++ program where initialize. So it is actually initializing size. See this. So initialize matrices. If we are actually put some sort of a message here, then it might be good as well. Okay, so it didn't put a message, so probably yeah. See this. Yeah. So matrix size serial time 11889 and parallel executor time 11441. Okay, millisecond. Speed up 1.7. Okay, maybe what we will do here is so it may not taking much time. So maybe what I will do here, I will put one more thing, initializing, so something like that. Okay, so might be easy. Okay, maybe we will put it like this. Okay, so that might be easy. Okay, maybe so the speed up is previously the speed up was less. Okay, so maybe we will try to run it again one more time. It is not taking much time, so let me show you that. So matrix size, sorry, let me close it. Initialize, let me put it as initializing. Okay, initializing matrix size, so something like that. Okay, then I will try to run it. Okay, so initializing the matrix size. So let's see. Yeah, so it is actually initializing as 1000 by 1000. Okay, so and then it is actually doing the serial multiplication as well as doing matrix multiplication parallelly. Okay, so doing the task. Okay, so let's see what actually it's going to display, the speed up time. See this. Okay, serial execution time is going to be 12281 millisecond, and the parallel execution time is going to be 10667. Okay, and the speed up is 1.15. So there is a speed up. Maybe we can try with the try instead of we can 1000, we can try with 1500. So probably the speed up will increase, but I don't know how much execution time it is going to create. Okay, so that's another challenge. Anyway, let's try it. Okay, and let's see what actually going to happen. Okay, probably it might take a bit more time because the serial execution is going to be much longer compared to the parallel execution time. Parallel execution must be much less. Okay, so as the size increases, the parallel execution, you can see that the parallel execution is, or OpenMP is going to take effect much more better than you can see it in the serial execution. Okay, let's see. So probably it might go a bit more time, I believe. Okay, maybe we can even try to see the task manager as well. Maybe we will see some of the things which is going on behind the scene. Okay, so how much time it is going to take? CPU, memory, performance. So one CPU. Anyway, so it's taking too much time. I think serial execution is going to take too much time rather than the parallel execution time. Okay, so maybe see this. So 1000 by 1000 matrix was a pretty reasonable thing. Don't know whether this is actually going to take it too much time. Seems to take more time, I think, once it goes above 1000 matrix, 1000 by 1000. Anyway, let's wait for a few minutes as well. Okay, let's wait for that. Yeah, so it came. Now we can see the speed up. Let's try to see the speed up. See this. Okay, serial execution time 5.3, parallel execution time 5.7209. Okay, so it's actually it's actually higher now. So some of the things it's actually in the other direction. Okay, so it's important that you need to tune the things in a much better way. Okay, maybe ABC, multiply matrix by serial, multiply matrix by parallel, matrix size, serial execution time, parallel execution time, speed up. Results match, yes, no. Okay, maybe we will run it again. Okay, maybe we will run it with 1200. Okay, maybe we will probably we can use other things as well. Pragma 4 size. See this IJK. Let me see for 1000. Let me see what is actually going for 1200. So we might need to properly tune it. So that's another aspect. Okay, even if you put the put OpenMP support, there you also might need to tune the matrix size and other things as well. Okay, so we cannot automatically get the speed up. That's another challenge which is going to be here. Okay, so that's what exactly happened when I tried it for 1500. Now let's try it for 1200. Okay, sometimes this is actually taking more time than what is actually expected. Let's see. matrix size is again yeah. So here also this speed up is much better. Okay, so it is 1985 milliseconds, but parallel execution time 16478 milliseconds. So there is a speed up of 1.2. Okay, so there is a speed up. Okay, so that is one aspect regarding OpenMP. Okay, so let's so one more thing I just want to show you here is there are certain situations in which you might need to develop code straight in assembly. Okay, so that is one thing probably. So we can directly code from a C++ environment, C or C++ environment. We can directly code it in assembly if it is really needed. Okay, if it is really needed, if the compiler is not supporting the special instruction sets, then there is a chance, there is a possibility that we can straight use assembly code. Okay, so in that case we are actually going to use a keyword called assembly ASM. Okay, ASM keyword. So so what we will do here is we will ask Grok to develop a program where it also shows how to use the ASM keyword. Okay, please also develop a routine which show how to develop develop assembly code routine which show how to develop assembly code using keyword underscore ASM. So inline assembly code is actually using assembly ASM. Okay, develop a routine which show how to develop, so it might be developing. Okay, so probably symbol routine, I might need to mention it as symbol routine. Okay, unfortunately I didn't mention it. Let's see what type of code it is going to generate anyway. Okay, yeah, it's trying to generate some code. ASM keyword, yeah. So it is actually ASM keyword is actually specifically for VC++, MSVC. Okay, so maybe yeah, for adding two numbers. See this. Okay, so this is how function to see this. Okay, so this is an inline assembly code. Okay, so let me put that inline assembly code on top of this and then explain it. So this ASM keyword is actually the one which is actually used to used for directly writing the assembly code. Okay, so this is basically the EX instructions, move instruction sets. All of you can add any sort of instruction sets here. Okay, if it is actually needed. So this is called inline assembly, and where we can directly call it. So like any other code, you can we can use this assembly code. So what we will do here is we will demonstrating inline, so we will put this thing as well. Okay, so we will put that routine as well. Okay, so let's try to run this application. So we can call it like any other functions. Okay, any other normal functions, this inline assembly code. So it's actually used, this assembly code is actually used to add two numbers and return the results. Okay, so that's what this is run. Let's try to run the application now. Okay, so let's see what actually happens. Okay, some problem, maybe error before EAX, so probably not supported in this architecture. ASM is not supported, that's what it's actually. So probably so we might need to missing before EAX. Maybe we might need to we might need, this is actually, let me see, yeah, maybe we will comment this is a comment actually. Okay, so let's see. Okay, let's try to run this now. Okay, so now it's okay. Okay, so just what happened, EAX and EAX, it should be okay. What actually happened, EAX undeclared identifier, maybe we might need to add some more thing. Okay, here OMP chromo vector, maybe we will ask grok itself. Okay, so hopefully this will be, so it will try to fix it, okay, for us. Okay, maybe something is also missing, so let's try actually. So let's OpenMP multiple IXM block. Okay, yeah, so I think if def, okay, x86 in results, else return a plus b. So likewise something is actually needed. Okay, x86, so that we didn't mention it here. Okay, maybe let me check. Yeah, so probably we might need to put like this. Okay, so this is not x86. Okay, so architecture is more, EAX is actually 32-bit. It's not a 64-bit architecture, it's a 32-bit architecture. So let's try to first run this thing, then we will change it to 32-bit. Okay, so it run. Okay, yeah, so that again the other thing, matrix size and other stuff. Now just a minute, let it run. So this is actually in the 64-bit architecture. Now we will change it to 32-bit architecture and see whether it is actually working. Okay, so that is another thing, taking a bit time. Maybe our just a minute, slicing. Maybe this is not our yeah, it's already done. It's again the speed up is there. See this. Okay, 1.11. So let's try to put it into x86. Okay, so this will be enabled. This will automatically enable now. This should enable. See this. Okay, so IM x86 means 32-bit architecture. Okay, so it is already enabled. Let's try to compile it now. So it actually compiled. See, so it actually used the assembly instruction set. Since this is actually 32-bit instruction set, you might need to set it as x86. Okay, so if it is 64-bit instruction set, then you need to modify it accordingly. Okay, so this is what inline assembly is all about. Okay, so if it is really needed, okay, I'm just telling you, if it is really needed, most of the compilers will generate really beautiful, really good, high quality assembly internally machine code. Okay, so there is no need for you to use these assembly instructions directly. And if it is really needed, sometimes there are specific instructions in the processor architecture which probably the compiler will not support. In that case only, you only need to use these sort of things. Okay, so that's it for this tutorial. If you are having any sort of doubt, please do let me know. I will be back with another tutorial if needed. Thank you.